Yes. That would generate that? Yes. I don't know what the shape would be, but yes, it is. An application of your question, there's an engine called a rotary engine, or it's called a Wankel engine, the Mazda RX-9 or whatever they have now. Mazda RX-6s were the first one that did it. It has a shape inside. It's like a triangle with curved sides, and as it rotates, it rotates through this chamber that is a unique shape that if I graphed it out instead of circular, but horizontally like this one right here, it would generate something that looks like that. Yes, there's a generator, a shape generator that would make that thing. I don't know what it is, but yeah, there's a shape generator. All right, I think we are going here. We are going, so I apologize to Leo. You can ask why it's Joel's fault in a little bit. Not really. I forgot to hit the record. So, Leo, sorry about that. You're going to have to come back and get help from Joel on the first one right over here. All right, we're in the middle of example number 3. We figured out it was periodic by adding a value 2 pi that when I simplified it, reduced back to my original equation. Graphically, we looked at it, and it repeats itself twice in this 4 pi length, so the period is 2 pi. And then it says state the domain and the range, and then it says sketch 2 periods of it. Well, right over there, we did 2 periods of it when we looked at the graph. But the domain of this, what is the domain of this sine cubed of x function? Yeah, anything, all real numbers. I can put in, it's heading forever to the right, forever to the left. I can put any values in it. So my domain, and I'm going to write it as an interval because it's the easiest way to write these things, negative infinity to positive infinity. What is the range of this one? -1 is as low as we go, +1 is as high as we go, including those values. So our range is from -1 to +1 is the range of this function. Back over here, what's that? Is it 1.5? We are going to verify if that really is the case. They say 1.5? Can't be 1, 2, 3, 4, 5. All right. The window size, the window they were looking at, yeah. As we look at it right here, we can say, oh yeah, oh I can't draw on it, I forget. That's +1 to -1. There's that same graph. And it just keeps going on and on and on and on. So it just keeps on repeating that cool pattern. So there are many things that are periodic, different shape, but still periodic. Somewhere back here, there we go, is my original. Now, looking at powers of x, we had sine cubed of x back over here. Sine to the 4th or the 5th or the 6th or the 7th all have a unique shape that goes along with them. Let me just clear that out, I guess. Here, this blue one was the sine cubed. The black one is the normal sine graph. If I graph sine to the 4th of x, it looks very similar, but it just gets, as I put it here, for lack of a better way of expressing it, sucked in more in that bump, in that maximums and minimums that come along. Same period as sine of x, and higher powers just get sucked in more and more and more. Analyzing. Now we're looking at non-negative ones, because negative ones just reflected over the x-axis, so they might look a little bit different. Find the domain, the range, the period of each of the following functions and sketch a graph showing 4 periods. Absolute value tangent of x. What does absolute value do to anything? Keeps it positive. If it was negative, makes it positive. If it's positive, stays positive. So nothing is on the negative side. Now let's think just a minute about what the original tangent graph was like. Here is pi over 2 and negative pi over 2 and vertical asymptotes at those locations, and my original tangent graph looks something like this. And then it keeps repeating itself. So another pi, which would be 3 pi over 2, Should have had these in red. I'm going to keep this. Negative pi over 2. And it would just keep repeating itself, going along like this on both sides, etc. So there's my tangent function. Well, if absolute value keeps it positive, it means this part, I'm okay. I can keep that part. But what will it do to this bottom half? We'll just flip it up, reflect it. So it's positive. So absolute value tangent graph is going to look like this if I graphed it out. Absolute value of the tangent. This makes the negative part positive. Domain. So what's our domain of this one? Well, I can't have certain things. So I have all reals except, let's not even just say, let's just say x cannot equal, where's the first place I cannot equal? Pi over 2, and then odd multiples of it. 1 of them, 3 of them, 5 of them. X cannot equal odd multiples of pi over 2, my domain. How about my range of this one? Look at the range. What's the range of this one like? I agree. 0 to infinity. Starts at 0 and heads up towards infinity. There's our range of this one. So sketch a graph showing 4 periods. Oh, here's a graph showing 4 periods right over there from the calculator. So I just happen to have 3 periods on mine, but you can add another one in. Absolute value sine of x. Okay, well, we know absolute value makes it positive. I know that a normal sine graph looks like this as I go along. Did I do that right? Nope. I got off over here on this side. Maximum come through, minimum come through, maximum come through. There we go. All right. So there's my normal sine graph. So absolute value, well, if I start here, I'm good right there, then what's going to happen with this bottom? Yeah, it's just going to reflect it over. It's going to be positive. So here it is. This is my absolute value sine graph. And we were supposed to answer all the other questions. Domain. What's the domain of this one? All reals. What's the range of this one? Correct. It goes from 0 to 1. And, oh, that's it, isn't it? Oh, and sketch 4 periods? No problem. We want 4 periods. I can go negative 2 pi to 2 pi. 1, 2, 3, 4. Because what is the period of this one? Only pi. Because it just keeps repeating itself every pi length. I think I did it. There you go. There's 4 of them. So there's the absolute value of sine. So this stuff isn't so bad. Adding a sinusoid to a linear function. Here is a sinusoid, sine of x. We are adding a linear function, 0.5x, 1/2 x. That's just a line with slope 1/2, positive 1/2 slope. Well, what happens if I think of sine of x? It starts, or what's its maximum and minimum values? What's the maximum value of sine of x? How high does it go? 1. What's its minimum value? Negative 1. This is going to oscillate between the line 1/2 x plus 1, that's the maximum value my sine of x goes to, and y equals 1/2 x minus 1. That's the minimum value my sine of x goes to. So if I think of that, there's 1, my y-intercept, a slope of 1/2, so maybe it looks something like that. Here's negative 1, my y-intercept, a slope of 1/2, goes something like this. What is the value of sine of x at 0? What's sine of 0? Remember at 0 radians? Sine function. Oh, it's on the same page. Let me come back up here. Sine function at 0 is 0. Then it goes to a maximum at pi over 2. Then it's back to 0. So what happens down here is when I am at 0, then it's just 1/2 x, the line 1/2 x. Well, that'd just be right over here. The line 1/2 x plus 0 has a y-intercept of 0. And then this thing is going to look like a sine graph that oscillates between those two lines right over there. And your graphing calculators are tremendously helpful to see what happens on this. But you pick up, hey, there's two boundaries to this one as it goes along. How do I know if when I combine two sinusoidal functions, is their combination a sinusoid? Now let's remind ourselves what a sinusoid is. A sinusoid is any graph that looks like a sine graph. So this black dashed line is a sinusoid. Now I can change the amplitude. I can stretch it and shrink it horizontally. I could reflect it. I can change, what else am I going to do? That's about all that I can do to it. But it looks like a sinusoid, just going up and down and up and down. So what happens if I combine two of them? Sums that are sinusoid functions, the rule is real simple. Sums and differences of sinusoids with the same period are going to be sinusoids. So where do I find the period? Remember, we have a formula for period right there. Is that formula 2 pi divided by absolute value b? So really, as long as my b value is the same, then 2 pi divided by b will be the same. So as long as my b value is the same, when I have two sinusoids that I'm adding together, it's going to be a sinusoid again. So if I look at this sine that has a b value of b, and this cosine that has a b value of b, well, those are, when I combine them together, going to be a sinusoid with a period 2 pi over b. Let's try it out down here with some numbers. Do we have, somewhere I lost my, oh. Do we have a sinusoid when we are done adding these? Determine whether each of the following function is or is not a sinusoid. Well, I look at the b value. 1. Yes, that's a sinusoid. Right over here, b value, no, that's not a sinusoid. Right over here, no, that's not a sinusoid. Right over here, 3/7, 3/7, 3/7. Yes, that's a sinusoid. When I get done doing all those things, it would just be like a sine graph. I'm going to illustrate that one. What is this? Example number 6. So let me close out these things. Let me go all the way down to example number 6 for a minute. Here are those 4. Remember the first one, I have the same b value. It should be a sinusoid. There's the graph of it. It looks like a sinusoid. Looks like a sine wave. The second one, my b values 5 and 3 are different. It is not a sinusoid. Is it periodic? Look at that for a minute. Yeah, I'm repeating the same pattern over and over again. So that is periodic, but it's not a sinusoid. It's really cool out there. And this really comes into play when we talk about music and physics. But anyway, this one over here, 3 and 2, no, this is not a sinusoid when I put them together. Is it periodic? Ooh, it appears to be. I appear to be repeating that same shape, don't I? Keep on going, kind of like this W thing that's going on. So it's periodic, but it's not a sinusoid. And this last one with all those 3/7, yes. And hey, sure enough, this thing is a sinusoid that just keeps repeating on and on and on. It's just a big one, but it's a sinusoid. So that's what we are talking about. Now, let me illustrate on this last one. Why won't it let me grab and drag that? They didn't tell us what on this thing, where'd it go? Right over here. A, B, C. We don't know the amplitude values of each of these, but it doesn't matter what A, B, and C are. They can be anything, and I still have a sinusoid. So the cool thing that I can do right here is I can start changing that A. Yeah, it's going to change the amplitude. I could even change the B at the same time, or change the C at the same time. And you can watch this thing change, but it's always a sinusoid. It doesn't matter what my A and my B and my C are. And if I had my window a little bit bigger, you could see that, hey, sure enough, this thing is a sinusoid. So let's just make my window a little bit bigger. Negative 20 to 20. Now you can see a little more of it. And as it comes around, yeah, it's just a sinusoid of all different shapes. Or I should say, of all different sizes, not all different shapes. All right. Express the sum of sinusoids as a sinusoid. So looking right here, we have a sum of a sine function and a cosine function, but their b values are both the same, and so it should be just a sinusoid when I add these together. So first they ask us, what is the period of this function f right over here? What's the formula to find period? 2 pi over absolute value of b. What's my b value? 1. So what's 2 pi divided by 1? 2 pi. There's the period. This has the same period as a normal sine function. Estimate the amplitude and phase shift graphically to the nearest hundredth. So when I graph this, and I'm going to do it back over here, when I graph this one, so here's the one that they have given me. It's like, oh yeah, this thing does look like it's just a sinusoid. Now I'm going to change my x-axis a little bit again. I'm going to go negative 2 pi and positive, whoa. Let's not do a summation notation. Negative 2 pi to positive 2 pi. So here's my sinusoid. It has a period of 2 pi. If I look where it starts here at 0 to 2 pi, that shape is repeated back here, negative 2 pi to 0. So I'm seeing 2 of the periods going on. Now they want us to estimate, maybe I need to keep it back here. I love that graph thing, but maybe I'll keep it back here, easier for you guys. The amplitude and the phase shift graphically to the nearest hundredth. Get your calculators out. Let's do it that way, because you all have that on them. Make sure you're still in radian mode. And we are going to graph this original 2 sine x plus 5 cosine x. And I'm going to do zoom trig, which is choice number 7. And then I'm going to adjust it a little, but at least I get my original picture here. So let's go to my window. I'm going to adjust a little. My minimum, I'm going to say negative 2 pi, 2 pi, negative 2 pi to positive 2 pi. Now that scale, 1.57, that's already pi over 2. I'm going to leave it. Now my minimums and maximums, I wasn't tall enough in the y direction. So let's go maybe negative 6 to positive 6. See if that one's big enough. There we go. Looks like we've captured it. So the first thing I need to do is I am supposed to write this thing as a sinusoid. Well, sinusoids, y equals a sine b, parentheses, x plus h or minus h plus k. So that's the complete manipulation I can do of any sinusoid. Now, I want to start out by this plus k. Do we appear to have shifted it up or down any? No. And we could verify that by doing the next part that's going to help us out. I want to know the amplitude. I want to know how high it goes. So I need to find a maximum of this. So calculate the maximum, choice 4. Left bound, right bound. And it says, hey, x of 0.38 is where it occurs, and the maximum is 5.385. 5.39. So I have my maximum or my amplitude 5.39. And we're going to write it as a sine graph again. To verify that it hasn't moved up or down at all, I could calculate a minimum, choice number 3. And so I'm just going to go somewhere. It doesn't matter which minimum I pick. Hopefully I didn't go too far. Right band, left band, negative 5.39 covers it up. Same thing. We haven't shifted at all. So I am going to eliminate that. I don't have any of that thing going on. So I have my amplitude. My period is still 2 pi. My b value originally was 1. My new b value is 1. Nothing's changed on that. So I just need to change my h, or figure out what my h is. How far have I slid one way or another? Well, normally a sine graph is heading up at the origin. So we apparently have slid it to the left some distance. So I'm going to figure out where this first 0 is to the left, and I'll figure out how far to the left I've slid it. So I'm going to calculate the 0, choice number 2. Left bound to my 0. I got a ways over there, didn't I? My right bound. I think it's somewhere in between. It is negative 1.19. Well, if I am going to slide it to the left, what will I need to do with this h? Plus 1.19. So what I really have is, I can have a new function, maybe I'll call it g of x, that is 5.39 sine of x plus 1.19, because I didn't have any b change. That should be my sinusoid. Oh, look, that's what they wanted on the next line. That should be my sinusoid that approximates it. So how well did we do? Well, hit y equals, come down to your second equation, and let's enter ours. 5.39 sine of x plus 1.19. Close it all up. What should I see when I graph? Yeah, there's the original, and there I'm running graphing the new one. Do you see anything different? No, we matched it up. We've got our new graph. So once we know that a sum or a difference is going to be a sinusoid, we can graph it, and we can calculate the amplitude and where our phase shift was and fill it in. We're done. And if I translate it up or down, we can figure that out too. Showing a function as periodic, but not as sinusoid. Remember a minute ago, we graphed this thing, sine of 2x plus cosine 3x. Let's look at it. Sine 2x, cosine, sine 2x, cosine 3x. Sine, oh, I thought I had it. Oh, well, not there. False alarm. Is it periodic? I'm going to algebraically do the same thing I did a little bit ago. I'm going to take sine of 2x and call it sine of 2 times x plus 2 pi. As long as I can add something to the original, 2x plus 2 pi. As long as I can add something to the original and I get the same answer when I simplify it, then it is periodic. Now, I don't know if the period is 2 pi, but that's the one we pick because we know that sine and cosine are periodic with a period of 2 pi. 3x plus 2 pi. Okay, well, I know that if I have the sine of any value and I add the period of sine, which is 2 pi, it just repeats the same value. So I can replace this with sine of 2x. And same thing's happening over here. Cosine of any value, if I add 2 pi, since cosine has a period of 2 pi, it's going to be the same value again as the original cosine of 3x. Yes, it's periodic. Is its period 2 pi? I don't know. If we graph it out, this one happens to be this shape. I ended at the same height I began right over there. It happens to be a period of 2 pi. Now I'm going to pull example 8 back over here so we can see more than just one period of it. Why it doesn't recognize it when I do it here. So here is that same graph, and it's 0 to 2 pi on the right half side. If I change the color, can you tell that that's green and that's yellow? Notice that green and that yellow are exactly the same shape. They have just been repeated. So it's periodic. It's not a sinusoid, but it's periodic. And this is from the sum of two sinusoidal waves, a sine of 2x and a cosine of 3x. I want to relate it a little bit to music real quick, just because it's so cool. If you play an instrument, you get, if it's a pure tone, or I should say a tuning fork, you just get a sine wave. But if you play the same note on an instrument, whether it's a guitar, a flute, a trombone, whatever it is, you have the same period because it's the same note. The frequency, how often it repeats itself, is the note that you hear. But the shape looks different because it's a combination of several, they're called harmonics. You have heard the term if you're in music at all. Several harmonics played together at the same time. It's an addition of several things because each instrument has its own unique combination of harmonics of any note you play. So when you play a flute middle C and a trumpet middle C, they're both middle C, and a violin middle C, it's still the same note middle C, but they all sound different. They have a different tone to them. And it's because of the different shape of the graph that repeats in the same period. So our ears hear the period, which technically is the frequency. 1 over the period is the frequency. We call it frequency. Our ears hear the frequency, and we call it middle C, or any other note. But our ears also pick up the variations in the frequency. We can tell it's C, but we can tell it's a violin. So I think it's pretty cool. Music is just math, in case you ever wondered. Damped oscillation. The last thing we are going to do is multiply a polynomial times a trig function. And here's what always happens when I multiply a polynomial times a trig function. I damp the trig function, or I squish it, is what's happening right here. What shape is x squared plus 5? What shape is that polynomial? It's a parabola. What does the plus 5 do to the parabola? Shivs it up 5. If you look at this red right over here, that location happens to be 5. That's the parabola, x squared plus 5. This location down here happens to be negative 5. It's the inverted parabola, the reflected across the x-axis parabola. And what is a cosine? Now 6 changes the period, how frequently it goes up and down, but this is just a cosine graph. A cosine graph, remember, is normally at its peak, and it's going like this. There's a cosine graph. Well, it's real fast. Look right here at this blue one. That's a cosine graph. But it is bounded by that polynomial and the inversion of the polynomial, the x squared plus 5 and the negative x squared plus 5. Now the red doesn't show up when I graph it. Only the blue shows up, but the polynomial is the boundary of it. And wherever it is squished, we say it has been damped, D-A-M-P-E-D. It is damping that is going on. So how is this one damped? It's damped as x approaches 0 from the right and from the left. From the right and left. As I approach 0 from the right, I get squished. As I approach 0 from the left, I get squished. If you go farther and farther out, this thing just gets bigger and bigger and bigger on both sides of it. Damped oscillation. is any time where I have a function, a polynomial function, times a trig function. It doesn't matter whether it's time cosine or sine. It's time a sinusoid is what's happening. And it always will oscillate between the graphs of positive f of x, that polynomial, and negative f of x. So we have damped oscillation, and that function is called the damping factor. How much is it squished? It's squished according to that x squared plus 5 graph. That's where it's squished to. Those are the boundaries, called the damping factor. Identifying damped oscillation. For each of the following functions, determine if the graph shows damped oscillation. And if it does, identify the damping factor and tell where the damping occurs. So as I look at this, here is my equation I'm multiplying times my sinusoid. Now let's see if we can figure out what this shape is, 2 to the negative x. Do you remember what shape that would graph as? Let me throw out the negative. What if I said 2 to the x? Whoops. It is a what? Just 2 to the x. Y equals 2 to the x. It's an exponential. Y equals 2 to the x is just an exponential growth. A negative up there is a exponential decay. Here is an exponential decay graph. That's 2 to the negative x. Now that is my damping factor if it really is squishing it. This one and the negative, I invert it, the reflection across the x-axis. A sine graph. Oh, I know what a sine graph looks like. It's normally right here doing this. This one appears to be squished. It appears to be squished as I head to the right. So yes, it is damped oscillation. And as x approaches infinity, that's where I'm getting squeezed. There's the graph of it right over there. So I'm getting squeezed by this 2 to the negative x and negative 2 to the negative x, those two black dashed lines. Here I have 3 times my trig function. Now what does the equation y equals 3 look like? Just like over here, I pulled it out front. What is that? Don't make it hard. That's an Algebra 1 question. What is it? Just a horizontal line. That's all it is a horizontal line. 1, 2, 3. There's a horizontal line. So if I also graphed y equals negative 3, 1, 2, 3, a horizontal line right there. And I know what a cosine is like. A cosine is maximum here. Now remember that 2x is just going to change my horizontal stuff. So I'm not putting any scale to it. Is that being squished anywhere? No. It is just oscillating between the 3 and the negative 3. Now we already knew this graph from another method. What do we call this number in front when I'm talking about sinusoids? We have a name for it. It's the amplitude. This is just a cosine graph with an amplitude of 3 is all that it is. But it ties in with what we're learning here. It all fits together. So is this one damped? No, because it's not squished. Now it is bounded by the y equals 3 and negative 3, but it's not damped. So there you go. It's just a normal graph. So let's try this one. Again, I'm going to pull this out. What is the shape of the graph y equals negative 2x? Don't make it hard. It's a simple graph. It is a linear graph. What's the negative 2 stand for in that line? Yes, you guys are all thinking of the complicated descriptions of it. Slope of negative 2. You're right, it's reflected and vertically stretched by 2. I mean, that's all true. It's a slope of negative 2 with a y-intercept of 0, right? So, slope of negative 2, y-intercept of 0. And the negative of this, well, the negative of a negative 2 is a positive 2x. Well, that's just a line, y-intercept of 0, and slope of positive 2, like this. What's the thing right here? That's a cosine. Now, if I am going to have to be between these lines and they have both collapsed to 0 right in the middle, My thing is at 0. And I am then bounded. Is this one squished or damped? Yes. It's damped as my x is approaching what? 0. As x is approaching 0. I'm not going to put the plus and minus from both sides. As I'm approaching 0, I am squished together. So here they have it. Let me pull it out on a bigger graph that looks so much cooler. I need to remember which one this was, example number 9. So if we'll turn off those things and we'll pull in our, okay, remember this is the original graph, and here, oh, that's the very first, the original one. Sorry, I wanted to do the last one with that x in the middle, didn't I? If I look at that last one, negative 2x cosine of x, if I added in, just real quick, y equals negative 2x. There's the boundary. And if I added in another one, y equals positive 2x. There's the other boundary. And if I zoomed out, there it is. It's bounded by that thing. And there it is, flopping up and down in between. Or oscillating in between. Yeah. All right. Last thing is we are going to apply this damped oscillation idea. Some of you in physics, we did a lab where we had a mass setting on a string, and we lifted it up, and we let it bob up and down, and we measured energies on that thing. Well, that slowly slowed down. We slowly lost energy because of friction in the system. We can actually model the actual, including the friction that is going on. Here is Dr. Sanchez's physics class. They collected a table. It happened to be an air glider that oscillates between two springs, so it's bouncing back and forth is what it is doing. And they came up with this equation. Pick out the function in front of my trig function, and that function in front is the boundary. Now, can I recognize it? E to the negative 0.065t. This is an exponential decay. So that's going to change the amplitude of it, etc. But that's the exponential decay. So I've got some sort of graph that's doing this, exponential decay. And then the negative of that, I just flip it over. It's doing this. And that cosine, 2.4t, is how often it oscillates, but it's just a cosine graph. So I know it's going to start at my maximum right here, and it's going to oscillate between these things, getting smaller and smaller and smaller as it goes along. It says identify the damping factor. The damping factor is the equation 0.22e to the negative 0.065t. That's the damping factor, the equation that is the boundary. Tell where the damping occurs, we'll just look at this little graph. Where does the damping occur? As x heads to infinity, that's where I'm squeezing it. And it keeps squeezing it smaller and smaller and smaller as I go that direction. Approximately how long, approximately how long does it take for the spring to be damped so that my y values, my values oscillating up and down in the y direction, is going to stay between negative 0.1 and positive 0.1. Well, I even did the link to the Desmos graphing calculator over there. But let's pull it up. Turn off our cool things down here. Whoops, turn off. Okay, here is our original graph is right over here. And here are the two boundary lines. I'm going to put in the boundary line. There's the original one, and here's the negative of it. So there's my boundary. Now I'm going to change my scale a little because look how squished. I mean, I can't even see the thing right over there. So I'm going to change my y to be a whole lot smaller. In fact, if you remember that question, it was between negative 0.1 and positive 0.1. Well, I'm going to go to negative 0.3 and positive 0.3. Whoops. jump too far. And positive 0.3. I can just let it decide what it's going to do. Did I not change my y's? Did I change the wrong thing? Oh, I changed my x, didn't I? I'm going to go from -5 to 25. Now let me change my y. -0.3, positive 0.3. There we go. Now I can see it a whole lot better. That's inside. Now I'm going to go and I'm going to turn on that function right over here. So there it is. Notice right at 0 it starts at its maximum. And there it's oscillating between those two lines. Now they had the question of, let's go back to our question. They had the question of my y values between -0.1 and positive 0.1. So I want to come back over here and I want to put in I'm going to turn off my boundaries. I'm going to put in y equals 0.1. There's that boundary. Whoops, turn off. And y equals -0.1. So where am I going to be oscillating between those two? Now I'm just going to make them the same color. And we'll leave it, let's leave them solid. All right. So where am I oscillating? Well, I notice I'm past it over there. I'm past it down here. Ooh, I appear to be less. Let me zoom in a little bit. Yeah, I'm less than that line. So I first, right at this location, I am first between my two lines and never outside of it. I'm outside of it as I move to the right until I get to that location. So I'm just going to select that, and I come right over here, and 11.859 is where I hit it. And anything past that 11.859, I am going to be oscillating between those values. 11.859. Let's pull it back up. We can do it on our calculator. There they zoomed in. There's your number, 11.859. That's the last location where I am between my lines. So as long as my x is greater than 11.859, I am going to stay oscillating between them. All right, that's today's section. Wasn't that fun, though? That was fun.